Chapter 4 is getting into the probability. So far, the first 3 chapters, we've really been just dealing with statistics, looking at data sets, how these data sets, how the numbers fall, how varied they are, frequencies, all that kind of stuff. And so now we're going to get into probability part of this class. Essentially, I want you to think of probability as the chance of something happening. Okay? A lot of times we think of probability when dealing with like gambling or like rolling a dice, flipping a coin, and it very, very much is that. But probability also lends itself to everything. Why insurance rates are higher for teenagers than they are for adults. It's because statistically speaking, the probability or the chance that a teenager gets in a car accident is higher than, say, a middle-aged adult. Why? That's just the way that it's been throughout the years. Insurance companies collect data, and they found that teenagers get in more accidents. And so the probability, since you are a teenager, that you will get into an accident is higher than, say, myself. It's kind of sad. That puts me as a middle-aged adult, but it's what I am. I need to accept that. So that's essentially what probability is, okay? Sometimes they will call it what are the odds of something happening. Same thing. Probability defines the odds of something happening, okay? So some examples of how probability is used, everything, like I said, from the chances that a certain play in a football game will work, the probability that you randomly get picked for a contest. It's endless where probability is used. Okay, a probability experiment is some process that will lead to well-defined results when that process is by chance. Okay, so a probability experiment would not be me throwing a dart at a dartboard. The reason is that's not by chance. My skill level has something to do with it. Whether I'm highly skilled or don't have much skill at all, it's not by chance. Okay, now if I roll a dice or a die, as long as that die is fair, and what we mean by fair is that it's not like one side isn't bigger than the other, or that it's got more weight on one side or the other, that it's a fair die, that's a chance process. It's by chance. You pick a gumball out of a machine. That's by pure chance. If you close your eyes, you kind of mix them up. That's pure chance. There's no skill involved in that. Okay, so probability experiment is something where it's by chance. An outcome is whatever happens from one trial. So let's say we have a giant tub gumballs. The outcome would be whatever color gumball I pick. That's one outcome. Okay. And then the trial is me actually going in there and like picking that gumball or flipping a coin once. So the trial is flipping the coin. The outcome is, was it heads or was it tails? Okay. And the process of flipping the coin, that could be an experiment if you do it over and over and over again. Sample space. The sample space is a set of all possible outcomes. So what could possibly happen when you do that experiment? So for instance, rolling a die. What are the possible outcomes that could happen when you roll a die? Well, pretty simple, right? You could get a 1, you could get a 2, you could get a 3, a 4, a 5, or a 6. So the sample space is always different depending on what the event is. In this case, rolling a die, you could either get a 1, 2, 3, 4, 5, or 6. So we'll quickly look at some other ones. If the experiment is tossing a coin, your sample space is getting a head or getting a tail. Like we just said, rolling a die, it's getting a 1, 2, 3, 4, 5, or 6. If you have a true or false question, your sample space is either picking true or false. If you toss 2 coins, what are the different things that could happen? How many you got? You got 1 thing, 2 things, 3 things, 4, 5 more? Well, you could get a head and a head. You could get a head and a tail and a head, or a tail and a tail. So what's the difference? Is head and a tail and tail and a head 2 different things? They are, because they're 2 specifically different coins. Okay, so why aren't there 2 heads? We don't look at those different because they're the same outcome. But a head and then a tail is different from a tail and then a head. Now, if in your experiment you decide that, hey, getting a head and a tail and a head are the same thing, that's totally different. That's fine. The way that you would count those is you would count them the same, but the sample space, you have to look at the 2 coins as different coins. Think of them as a quarter and a dime. All right? It's possible that the quarter could be the head and the dime could be the tail. It's possible that the quarter could be the tail and the dime be the head. So they are different. So what's the sample space of rolling 2 die? It's a little bit more complicated. There are 36 different outcomes. You could roll a 1 and then a 1, a 1 and then a 2, a 1 and then a 3, 1 and then a 4, 1 and then a 5, 1 and then a 6. And you could do that for all of them, a 2 and then a 1, 2 and 2. So there are 36 different outcomes. Again, you may say is like this one. Rolling a 6 and then a 4, the same thing as a 4 and a 6. It's not the same thing. The reason is these are 2 different die. Okay? So the order in which you do them does matter. Now here, why aren't there 2 6-6s? Because it's not different rolling 6 and a 6 or 6 and a 6. It's the same thing. It is different rolling a 6 and a 4 or a 4 and a 6. Okay, find the sample space for the gender of children if the family has 3 children. Use B for boy and G for girl. So what could the different possibilities, what different possibilities could there be? Here they are. You can have a boy, 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 girl, boy, girl, boy, boy, girl, 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 boy, boy, girl, boy, girl, 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 boy, girl, girl, girl. How do we know we have all of them? I'll tell you this is all of them. Okay? But when you're doing this, if you don't know how many there should be, how will you ever know if you find them all? That's a very good question. So we have something that will help you find these out easier and make sure that you have every single sample or every single outcome that could possibly happen. And that's called using a tree diagram. Okay, so what you do with the tree diagram, and you can do this from left to right, you can do it from up top to bottom, it doesn't matter. Yeah. So your first kid, so this is considered right here our first kid. What could possibly happen with our first kid? It could be a boy or it could be a girl. Now you have your second kid. So this right here is considered the second kid up and down, okay? So first kid, second kid. So if you had a boy the first time, it's possible to have a boy the second time. If you had a boy the first time, it's possible to have a girl the second time. Same thing down here. If you had a girl the first time, you could have a boy. If you had a girl the first time, you could have another girl. And then you do that again with each one of these. So this right here is considered our third child to all of these. So if you had a boy, you could possibly have a boy, or you could have a boy, and a girl, and so on. And now all you have to do is basically follow these lines. Boy, 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 girl, boy, right there. Write them all down, and now you know that you didn't miss any of them. So that again is called a tree diagram, and that'll make things a little bit easier for you with situations like this. And let me explain that it doesn't have to have only 2 like offshoots. You could have 3, you could have 4, you could have 6 with rolling die. So it doesn't only work if there are 2 options. It doesn't matter how many options there are. Last slide. Couple of probability rules that you have to know. So when you're talking about the probability of something, we usually talk about it as a percentage, right? Like there's a 50% chance that this would happen. I want you to think of that percentage as a decimal or a fraction. It's not too often as we're working with these numbers that we use percentages. When you display them, when you see them in like newspapers or on the internet, a lot of times they are put out there as a percentage, and that's fine. It's correct that way. But for our use, we're going to be doing a lot of calculations with them, and so because of that, we want to make sure that we keep them as fractions or as decimals. So the probability of any event happening, okay, we'll call that event E. So E meaning anything, getting picked, getting either lottery numbers correct, rolling a die and getting a 2, anything. The probability of any event is a number somewhere between 0 and 1. Okay? It could be 0, could be 1, or it could be any decimal in between. Probability rule number 2. If an event E cannot occur, so that means that, gosh, try to think of something off the top of my head. The probability that I can't even think of something good right now. Everything I'm coming up with is bad. The probability that a student thinks Mrs. Solomsas is a nice person. Never happened, right? No, I'm just kidding. The probability of, okay, rolling a die and getting a 7. Sorry, brain fart. I don't know why that was so difficult. But the probability of rolling a die and getting a 7. The chances of that are 0, assuming we're talking about a normal die. Yes, there are dice out there that have more than 6 numbers, but a regular 6-sided die, you can never get a 7. So that probability is 0. Okay? If the probability is certain, meaning it has to happen, that probability is a 1. Okay? You have a gumball machine and it has all blue gumballs in it, and you say, what's the probability of getting a blue gumball? Has to be blue. That's the only thing that's in there. Okay, that probability is 1. So these are 3 very, very basic rules. They may seem like duh, of course we know that, but they govern a lot of what we do in this chapter. So make sure you know these, make sure you know them very well. Okay, that's the end of the notes for tonight. Have a good night, and no, I don't want those. Have a good night, and we will see you on tomorrow's video.